Hi everyone, I'm Chris Tisdell and I'm a mathematician at the University of New South Wales in Sydney, Australia. And I'm really excited today to be sharing some of my recent research with you. In this presentation, I'm going to discuss approximate solution methods for fractional differential equations of arbitrary order. So essentially I'm going to introduce the idea of an approximate solution, and then I'm going to combine that idea with sequential arguments to form new approaches to so-called existence theory for solutions to initial value problems of arbitrary order. Now, one of the advantages in this particular approach over, say, existing approaches to existence of solutions, like fixed point methods, is the following. Well, the techniques are reasonably basic, and in particular you don't need a knowledge of functional analysis. So all that's really required for the research in this particular presentation is some understanding of uniform convergence of sequences of functions. Okay, well, this is the general problem we're going to be looking at. So it's an initial value problem. The dq can be thought of as a general differential operator of order q. Now, here q could be a whole number or it could be a fraction, and so equation 1.1 is sometimes referred to as a fractional differential equation of arbitrary order. Now, I know the font may be quite small here, so if you're watching this presentation online, please make sure you're viewing it in the high definition category. Okay, well, if q equals 1, then dq is just the regular differential operator from a first course in calculus. Okay, this t function here, t sub ceiling q minus 1, is just the Maclaurin polynomial of order or degree, ceiling q minus 1, of the function x of t. F is some continuous function, possibly nonlinear, and the a sub 0, 1, 2, etc. are constants. And you'll see in 1.2 we've got just regular derivatives here incorporated into our initial conditions. Now, one of the reasons for that was suggested by a mathematician called Caputo back in the 60s, and he argued that having just regular derivatives here is more natural from a modelling point of view. So they're the ones we're going to look at. Now, this general differential operator, dq, is known as the Riemann-Liouville fractional differential operator of arbitrary order q, where q is positive. Now, I'll give a full definition a little bit later. So we're going to look at this general problem and introduce the idea of an approximate solution to this general problem. And then we're going to apply the ideas to form so-called existence theorems for solutions to this problem. So essentially showing that under certain conditions, this problem has at least one solution. Now, the ideas in this particular presentation are taken from my forthcoming paper. Now, I've listed a whole bunch of references at the end, and I'll show you the reference list at the end of this presentation. Now, I'm not, of course, the first person to work on these general problems. I just wanted to quickly outline some of the other contributions that are noteworthy. Firstly, this paper by Dittelman Ford is very interesting. In that paper, several approaches to existence, uniqueness and approximation of solutions to this general problem can be found. And then after that paper, Lakshmikantham and Vatsala wrote a number of papers extending and putting forward alternative methods. And also these two books also contain quite a lot of theory on these ideas here. Now, just to summarise these sorts of contributions, they can be summarised somewhat as the following. Well, sequential techniques involving successive approximations, aka Picard iterations, and also classical fixed point approaches of Banach and Schauder. Now, like I said at the beginning, the approach here is a lot more simple than these fixed point approaches. Okay, well, to keep this presentation somewhat self-contained, I'm going to speak about a few preliminary definitions and a little bit of notation now. Okay, well, we define the Riemann-Liouville fractional derivative of order q of a function y as this definition here, and the fractional integral of order q is given here. Now, sometimes, just to save a little bit of space, this is written with this superscript c on the left-hand side of the d, and it's referred to as the Caputo derivative. So, I might use this in some places and I might use this in other places, just to save a little bit of space. Okay, well, when we talk about a solution to our original system here, we're talking about a function that is has a qth order fractionally derivative. It's a qth order fractionally derivative function, such that the graph of the function lies in the domain of little f, and of course the function satisfies the fractional differential equation and the initial conditions. Now, instead of dealing with the system 1.1, 1.2, a common approach in the theory of differential equations is to actually rewrite the original problem as one integral equation. And so this is what the following lemma concerns, and it's found in Kilbus's book. I'm not going to give the proof, but you can look it up. Let's say f is continuous, then the initial value problem 1.1, 1.2 is equivalent to this integral equation. Okay, so we're going to use this quite a lot in the proofs of the main results here. Okay, well, we'll still need a few more little results. The following result is essentially a minor variation of one of the lemmas of Diethelm-Ford. Essentially, this is a general Gronwall inequality. Let A, B and C be non-negative constants, and let ρ be non-negative and continuous. If ρ satisfies this kind of integral condition on this interval, then on that interval we have the following inequality for ρ. Now, this E sub q is just a special function called the Mittag-Leffler function. Of order q. Okay, now I haven't actually defined it. You don't really need to know what this is for the context of this particular presentation, but you can think of the Mittag-Leffler function as playing a similar role to that of the regular exponential function in just classical calculus. So this Mittag-Leffler function is kind of like a generalized exponential function for fractional calculus. Okay, well, our techniques are going to use sequential methods. So I'm going to talk a little bit about some basic definitions for sequences. Okay, well, we call a sequence of functions phi sub m uniformly bounded on some interval I if there's a non-negative constant v such that this inequality holds on the entire interval, and v is independent of t and m. we call a sequence of functions uniformly equicontinuous on an interval I if for every positive number epsilon there's a delta that only depends on epsilon such that the following holds. Well, if T1 and T2 are close together, then this is as small as we like. Okay? Now we call a sequence of functions uniformly convergent on an interval I if there's a function phi such that for every positive epsilon and every t in I, there's a natural number n such that this distance, or I guess the distance between the sequence and the function can be made as small as we want if little m is large enough. Okay, and finally, the Ascoli Theorem. We're going to use this in the proof of our main result. So let I be a closed and bounded interval and consider a sequence of functions defined on that interval. If the sequence is uniformly bounded and uniformly equicontinuous on the interval, then the sequence of functions has a subsequence, and that subsequence, the subsequence converges uniformly on the interval to a continuous function. Now I know this is probably very hard for you to see here, so this is just sigma sub m sub k. So I'm going to use that kind of notation for subsequences. Okay, well, let's look at the main results. In this section, I'm going to define what I mean by an approximate solution to the general initial value problem 1.1, 1.2. And the work is based on ideas from Cauchy and Peano, and their investigations go back to the 19th century. Okay, so for the case Q equals 1, Cauchy and Peano were the real innovators. Now, roughly speaking, the approach first involves illustrating that a sequence of approximate solutions to 1.1, 1.2 exist, and secondly, showing that of that sequence of approximate solutions, there's a subsequence that converges to an actual solution of the problem. So in this case, I guess the existence method can be broken down to the existence of a certain limit of subsequences of functions, okay, whose limit has certain properties. Now, if you're looking for more, there are two excellent books by Reed and Coddington and Levinson where they discuss the case Q equals 1. So I believe that the results in this section are new for Q not equal to 1. Even when Q, for example, is 2 or 3, I'm still that the results I'm going to show you are new, even for those special cases. Okay, like I said before, an advantage of this approximate solution approach over fixed point methods is that the analysis is reasonably basic. Okay, so all you really need to know is some idea of uniform convergence and the Ascoli Theorem. Okay, well, let's define what we mean by an epsilon approximate solution. Now, in this definition, I've got integral type here. Throughout this presentation, I'm actually just going to refer to these kinds of things as just epsilon approximate solutions. Okay, now the reason why I've got integral type in this particular definition is because in my paper, I also talk about derivative type solutions. Okay, so let's have a look. Define a function x as an epsilon approximate solution to our initial value problem on this interval if the following conditions are satisfied. X is continuous, f of s, comma x of s is continuous, and there's a non-negative number, epsilon, such that this is less than or equal to epsilon on the interval of interest. Okay, so you can see that if epsilon's 0, then actually, well, x would be a solution to 1.1, 1.2. Okay, well, the domain of little f in this particular presentation is going to be something like an infinite strip. Okay, now the following result is a reasonably abstract result, and it gives us conditions under which our general initial value problem will have at least one solution. So let's have a look. Okay, so let f be defined on this strip, and let epsilon sub m be a sequence of positive constants that converges to 0. If we have a corresponding sequence of epsilon m approximate solutions to 1.1 on this interval, for which there exist non-negative constants k and k1, such that this inequality holds for each m and for each t in this interval, then that sequence of epsilon sub m approximate solutions has a subsequence, again, x sub m sub k, with this subsequence of functions converging uniformly to a solution of our original problem. Okay, so it seems rather abstract, and it is. I'm going to show you the proof here. The proof is quite long, but I'll try to break it down into definite steps. Okay, so let x sub m be a corresponding sequence of epsilon sub m approximate solutions to our original problem on this interval, and define the sequence of functions r sub m via the following, where this sequence of functions z sub m is given here. Okay, so the idea is to show that x sub m has a uniformly convergent subsequence whose limit is a solution to our original problem. That's the guiding principle here. Now we're going to do that in kind of a roundabout way. The z sub m is going to play a pretty big role here. Okay, well, since f and each x sub m are continuous functions, it follows that this r sub m is continuous on the interval. And the first claim I'm going to make is that the sequence of functions x sub m are uniformly bounded on the interval of interest. Okay, so that's what's happening here. Okay, well, since x sub m is an epsilon sub m approximate solution, well, we have from this relationship here this inequality. Okay, now by assumption, epsilon sub m is a sequence of positive constant that goes to 0. So we can find a positive number, gamma, such that this is true, okay, because epsilon sub m must be bounded from above. Therefore, if we just take this with the Zm written in here and rearrange it, I can come up with this and then bound this by gamma and this because t is between 0 and a. And by assumption, the f satisfies this inequality here. So that's where this is come from? So if we look back, we can see that this inequality holds, our general Gronwall inequality, lemma 2.2, with the following choices. Well, rho is this, A is this, B is this, and C is this. So essentially, you can form an a priori bound on each of these epsilon m approximate solutions. Okay, so that's what this V is. Okay, so that's taking care of this claim here. Okay, so the next claim is to actually start working on this Z sub m. And essentially the claim is that this sequence of functions is uniformly bounded on our interval of interest and also uniformly equicontinuous. Okay, so I guess this is like another step now. So I guess that's a claim here, and now we're going to show that Z sub m is uniformly bounded and uniformly equicontinuous. All right, well, from this assumption, we can come up with the following. Okay, so let's move to our sequence of functions Z sub m and look at this. Okay, well, you can just take absolute values here and you know, move those in and bound this up and use this to form the following inequality. Okay, so yes, there is a uniform bound on this sequence Z sub m, and the next step is to claim that the Z sub m is uniformly equicontinuous. Okay, well, this is quite long, but I'll just give you a flavour of it. So we break it up into two different cases, q greater than 0 and less than or equal to 1. Suppose t1 and t2 are points in this interval with t1 not equal to t2. Well, if you just take one of these away from the other, and then with a little bit of algebra, I think what's happened is we've added in something, come up with the following, because f's uniformly bounded, so that's where the mu comes from, and you can get down to here. Okay, now if q's greater than 1, this polynomial has a continuous and uniformly bounded derivative, just a regular first order derivative there, and as such there's a constant L such that this inequality is satisfied. Okay, well, if you bound that up, you'll get the following, and in this part here we've assumed t2 minus t1 is strictly less than 1, so this is true. Actually, I guess that could be a strictly less than there. Okay, well, given any positive value, epsilon sub 1, we can choose a delta sub 1 to find here to ensure that this is less than epsilon sub 1 whenever t2 minus t1's less than delta 1. Okay, well, that was the case when this is the case. Well, if you just reverse those, so you just replace t2 with t1, you can repeat the argument again. Okay, so essentially you can combine the two cases and show that Z sub m is uniformly equicontinuous. Okay, so I guess that's the end of the previous step, showing that Z sub m is uniformly bounded and uniformly equicontinuous on the interval 0 to a. All right, well, under those conditions, we know that the Ascoli selection theorem holds, and therefore Z sub m has a subsequence that converges to uniformly to some continuous function. Okay, well, this may seem a bit strange now because what we're trying to do is actually show that this x sub m has a uniformly convergent subsequence that converges to a solution of our problem. But we've shown that this has a uniformly convergent subsequence. Well, we'll get back to that. Don't worry, we'll get back to that. Well, actually, from the relationship I just showed you here, we can see something that's quite nice now. Well, R sub m converges uniformly to 0 because it's bounded by the convergent epsilon sub m's. And we know that Z sub m sub k converges to some continuous function uniformly on the interval. From this, well, because this goes to the 0 function, this subsequence must also go to this continuous function. It must converge uniformly to this continuous function x. Okay, so in a roundabout way here, what we've done is actually show that x sub m, the sequence of epsilon sub m approximate solutions, actually does have a subsequence that converges to a continuous function. Okay? So I guess this is the next step now, where we've taken the fact that this is a uniformly convergent subsequence, and that implies that this is a uniformly convergent subsequence with the same limits. Okay, so the last thing we've got to do is show that this limit function actually does satisfy our original fractional initial value problem, 1.1, 1.2. Okay, so we need to explore the properties of this limit function now. We don't know what it is, but we can still investigate some of the properties. Okay, well, x sub m is uniformly bounded by v, this sequence, and so we must have its limit function, x, satisfying the same bound. And if we define this rectangular set, R sub v, as this, so it's something like the following. Then the uniform continuity of little f on this yields the following convergence, uniform convergence on this interval. So what does that mean? Well, it means that I can move this, if I move to the subsequence here, I can move this limit inside and I obtain this. Okay, so what does that mean? Well, essentially, what's happened is we've essentially we know that the limit, our limit function, must satisfy the following, and by lemma 2.1 we know that every solution to this problem must also satisfy our original problem lemma 1.1, equation 1.1, 1.2. Okay, so this is like the final step here, showing that the limit function x must be a solution to our original problem. Okay, well, let's go back and have a little look at the statement of the theorem. Where is it? Ah, here it is. So what does this tell you? Well, it's an existence result. And all it says is that there exists a subsequence that converges uniformly to a solution. Well, there may be more than one solution. Okay, so this theorem, although related to existence, it doesn't tell you anything about uniqueness of solutions. Okay, well, it is a rather abstract theorem, and the conditions may be challenging to actually verify. So I formulated the following result with much more easily verifiable conditions. So this is a lot more practical, this result. Let f be continuous. If there exist non-negative constants k1 and k and k1, such that f satisfies this, I guess, linear growth condition on the strip, then for each positive epsilon, there is a corresponding epsilon approximate solution to 1.1, 1.2 on the interval of interest, and as such, there's a solution to our initial value problem, 1.1, 1.2. Okay, well, this proof is a little shorter. The idea is to, the idea is the following. For each positive epsilon, what we're going to do is construct a corresponding epsilon approximate solution to 1.1, 1.2. And this ensures that we can choose any sequence of positive constants, epsilon sub m, such that epsilon sub m goes to 0 with x sub m a corresponding sequence of epsilon sub m approximate solutions to our initial value problem. So in view of 4.7, 4.2 will hold, and we'll have at least one solution to our problem. Okay, well, so let's construct a corresponding epsilon approximate solution to our initial value problem. All right, so let delta be positive and strictly between 0 and a, and define this function x on the interval of interest as follows. It's kind of defined in a piecewise manner here. Okay, well, for t on this part of the interval it's this, and for t on this part of the interval it's this. Now, again, this might be quite small to see. This is 1 on gamma, and the integral is from 0 to t minus delta. Okay? All right, well, the continuity of f in our assumption ensures that for each positive delta and all t in the interval, the function x is well defined and continuous for each fixed delta. Okay, well, you can show in a similar manner to the proof of the previous result that this function here is uniformly bounded on our interval of interest. And the bound is just coming from limit 2.2. Now this sort of linear growth condition then leads to the following. So we have this sort of bound mu, and if we define this function zeta on our interval by this, then we have the following, and this function here is bounded by this constant. Okay, so for all t in our interval, this minus this is just the following, and I know that I can make this less than or equal to what's up here. Okay, so what I want to do here is make this small. Okay, so for any given epsilon, if we choose delta such that delta is less than this, then this is going to be smaller than epsilon, and as such, our function x will be a corresponding epsilon approximate solution. Okay, it satisfies the definition of epsilon approximate solution. Okay, so that's the proof. A little bit shorter, that one. All right, so theorem 4.3 addresses a remark in Diethelm's recent book, which questioned whether or not the linear growth condition on f could be used to still obtain existence theorems. I think in Diethelm's book there, he uses a sublinear growth condition. Okay, by that I mean instead of having, you know, absolute p to the power 1 here, it'd be absolute p to the power alpha, where alpha is strictly less than 1. Okay, well, let's put some concreteness into the presentation and give an example to illustrate the ideas. Let's consider the following initial value problem. Here the Q is between 0 and 1. And it's claimed that this initial value problem has at least one solution on any closed and bounded interval 0 to a. Okay, well, it's just a matter of showing that the conditions of this theorem are satisfied for this particular right-hand side. Okay, so we have a special case of our general initial value problem with f given by this. The ceiling of Q is just 1 here, a sub naught's 1, and so on any strip, what we want to do is show that this holds and that f's continuous. Okay, so obviously the f here is going to be continuous, and it's just coming up with the inequality 4.7. So let's take this. Sine, of course, is bounded between -1 and 1, so I can come up with the following: t is between 0 and a. So 4.7 does hold with k equals +3 and k1 equals a. Also, of course, f's continuous. So what do we know then? Well, we know that theorem 4.3 will hold, and this problem will have at least one solution. So it would seem that from the proof of the main results here, that the choice of a subsequence of the x sub m is necessary. However, it's not if known that the original problem, 1.1, 1.2, has at most one solution. Okay, well, I'm going to leave you with some further reading. The results in this presentation come from my forthcoming research paper, and I'll put a link to the journal in the description when it becomes available. And I've also listed a whole bunch of references here. And I've referred to most of these, but if I haven't referred to some of them, then you can think of them as additional reading material. So I'll show you those one by one. Okay, I hope you enjoyed this presentation, and watch out for more research videos in the future.